Okay, great. So yeah, welcome back, everybody. We've got some fun stuff lined up for today. And I wanted to start just with like a couple quick announcements or sort of like a quick overview of the class. So as you might have seen, the stuff that we looked at for today's class, parametric equations, were very different sort of in flavor and feel than what we've done in the past. In particular, we had this huge, big section, I guess, on series, and we had a lot of work in series, sort of building up to Taylor series and the sort of powerful way that we can represent a function that we know and love using this appropriate Taylor series, which was an example of a power series. And so now we've taken a complete left turn. In part, that is because we have really finished our section on series. Right, we've sort of hit all of the highlights, and we have sort of seen the biggest way in which they are used, which are for these Taylor series representations of functions. So what that means for us going forward is that we'll actually round out the semester by looking at a handful of sort of smaller subtopics. And that means this is actually a good moment to talk about what the rest of the semester looks like. There are two additional topics that we include in Calc2. They could really, because they sort of stand alone, they really could have gone at different points throughout the semester, but I decided to put them sort of here at the end as sort of a winding down moment. And those are parametric equations, which we'll be talking about today, and polar coordinate transformations, which we'll be talking about on Monday. And what that really means is that as far as brand new material, like, sort of never before seen course content, we really just have today's class and then Monday's class, and then we are basically done with new material for this class. So what does the rest of the semester look like then if we have material today and we have material on Monday? Well, as you may or may not know, if you've been keeping on top of the syllabus, the next major event in the class is a test 3, which will occur next Friday. So that's 1 week from today. So essentially, I'm planning on teaching this class today. I'm planning on teaching Monday's class on Monday. And then on Wednesday, I was planning on having some sort of review session in class, right? I might prepare a few things to talk about, but I would also try to keep it open for questions and things like that. The third test will primarily cover sequences, series, and then these final two topics that are coming after sequences and series. One major question that's been floating around, and I know it was asked earlier this week, was a question of how do you look at a series and know sort of like what strategy to use to determine convergence or divergence? So how do you know, whether it's a p-series or if you have to make a comparison, what's the right comparison to make? And so barring questions from you all, I figured next Wednesday's class would be spent sort of primarily looking at that, but also sort of serving as a catch-all review session. So Wednesday's class would be a review session. Friday, we would not have class. Instead, that time would be used sometime during the day to take the third test. And then for the final week of classes, we would have a class on Monday and a class on Wednesday. Both of those classes would be an opportunity to review for the final exam, right? As a reminder, the final exam is cumulative. And so we would get to spend the time reviewing some of the earlier material. Maybe Monday we would take integration techniques. Wednesday we would take all of those different applications of integration. So, calculating volume, et cetera, et cetera. So, and then that Wednesday, not this upcoming Wednesday, but the following Wednesday, is actually the last day of classes, right? That puts us right in line with the end of classes. So that is the rough outline. It means we are really drawing close to the end of new material, and there will be a bunch of days sort of scattered throughout the rest of our time to review all of the stuff that we've learned. Yeah, I think that's really the major thing that I wanted to say. That also means, as a reminder, that because we only have about 2 weeks left in the course, this is really the time, like now is the time, to be looking over your old quizzes and trying to reassess them. So anything that still requires reassessment, please reach out to me and ask for a reassessment quiz. Yeah, the time is now. Don't put that off too much longer. Yeah, those are the announcements that I had as far as start of class things. I'll pause for a second, see if there are any questions, and then we'll jump into the material. So any questions?
Is there going to be a practice test available to take?
That's a great question. Question was, is there going to be a practice test available? I don't know. I guess I have not created a practice test for test 1 or test 2. We just jumped right into the test and we took the test, but we are in sort of a weirder setting now. I believe, shoot, I don't know. Let's say yes. Yes, Jose, I will create a practice test for you all. And that should not be a problem. I'll try to create that this weekend, post it to Moodle so you have lots of time to look over it. Yeah, you can hold me to that, send me an email reminding me to do that. Since you asked, I'm gonna task you to try to remind me to do that sometime this weekend, and I'll get that up to you by the end of the weekend or early next week. Yeah, I think that's a great idea. Any other questions? All right. Oh, cool. Yeah, so that being said, let's get into parametric equations. As we've said, it feels very different. It is very different than the stuff we've been looking at more recently. And as you saw in the videos, a parametric equation, right, or a parametric curve, I tend to use those words slightly interchangeably, although they are technically different. A parametric equation, or rather a set of parametric equations, is a pair of two equations typically written as x of t and y of t, right? And in this case, that number t was said to be the parameter. It does not have to be a t, right? We saw an example in the videos where it was an x of theta and a y of theta. It could really be any additional symbol that we could use as a parameter. But classically, we tend to use t. When we use t, we tend to think of that parameter as representing time. And then the observation we can make is that when we have a pair of these equations, so an x of t and a y of t, if I want to consider that as a set of ordered pairs, x of t comma y of t, right? This is describing, for any specific t value, we can calculate x of t, we can calculate y of t, and then the pairing x of t comma y of t is giving us a point in the xy plane. And so as we vary our parameter, as we increase or decrease t, let's say as we increase t, then this x of t is changing, this y of t is changing, and that's like describing the point in the plane as changing, right? Or as sort of evolving as we go forward in time. And so these parametric equations, when paired together this way, describe a curve in the xy plane, and that would, that is something I could call a parametric curve. So there's this close relationship between a pair of parametric equations and the parametric curve that they're describing. And what we saw in our work, in the videos ahead of class, were that we, were able to describe these parametric curves given a set of parametric equations. And we also saw an example or two, maybe just one example, in which we eliminated the parameter and converted our parametric equation back into an expression like y equals f of x. So we eliminated the parameter t, and we were able to rewrite this as a single function. Okay, just to set the stage and to maybe remind us a little bit of what we saw in the YouTube videos, I wanted to talk through an example in which we are given this pair of parametric equations, and we are asked to graph it, right? So describe the motion of the particle with position x comma y. That's really x of t comma y of t, as t varies in the given interval. So we have this interval of time here, and then we're given these x and y equations, these parametric equations. And so one thing I did in the video, which I'll do again here, is point out that we can explicitly graph these as a function, right? Specifically, we can graph x as a function of t, and we can graph y as a function of t. We don't have to do this every time. I wouldn't necessarily require that you do this at the start of a problem, but it's nice to remember that we can do this, right? That not only are we, or maybe that as a starting point, our parametric equations are really just two functions in which our independent variables are t, and then our dependent variables, we have this x as a function of t, and we have y as a function of t. So I always think that's really nice to keep in mind. And if we do that, we can see that this first equation, x is 3 plus 2 cosine t, right? Well, that's going to be just the cosine function. We're going to multiply it by 2. So 2 cosine t, right, that stretches the magnitude considerably. So we're going to stretch that magnitude, and then we're going to add 3 to the height of the function, right? So we get this transformation in which our function ends up being the cosine function, but stretched and then raised up tall. And so, of course, the regular cosine function, I'll just sort of do this quickly. The regular cosine function starts at 1, and it sort of looks like that. And so twice the cosine function starts up here at 2, and it just looks like an elongated cosine function, and it sort of looks like that. And then when we add 3 to that, so we raise it in height by 3 units, that means we're going to start up here at 5. We're going to drop all the way down to 1, and then we're going to go up. And so the regular cosine function kind of looks like this. Now, we are specifically given that there's a range on the t values that we care about here, right? T is supposed to go from pi over 2 to 3 pi over 2. And so we could actually explicitly mark off where that happens on this function. So t, let's think through this. Cosine function starts at its highest point at time equals 0. It's at its lowest point at time equals pi, and then its highest point again at 2 pi. Right, so 3 pi over 2 would be right here, pi over 2 would be right here. And then if we wanted to explicitly sort of denote that sort of domain that we're looking at, I think we're looking at this midpoint, we're going down, and then we're coming back up to that midpoint again. So the sort of restricted domain, this piece right here, means that I'm only looking at this lower piece of the cosine function. Okay, and then we can basically do the exact same thing, but for our sine function, or for our y function. So y is also a function of t. What we have here, y is equal to 1 plus 2 sine of t. And so the sine of t would have started at 0, right? We can play this game. Would have started at 0 and sort of gone like this. So 2 sine of t will start at 0, but go twice as far, or rather have a magnitude that's twice as big. And then so 1 plus 2 sine of t, right, would start up here at a height of 1. We will just add 1 to everything. So it'll start at 1, and then it'll end up sweeping through. Let me see, I might have made that too long. We'll end up sweeping through the regular sine function, but with a height that's twice as big. And so we end up with something that kind of looks like this. Right, notice that it would have gone from, if I hadn't raised it by 1, it would have gone from a height of plus 2 to minus 2. So now it goes from a height of plus 3 to minus 1. And that's going to be here, that's minus 1. All right, and then just like before, we can notice the restricted domain. So at pi over 2, we're going to be up here at its highest point for the sine function, and at 3 pi over 2, we're going to be at the lowest point. And so our restricted domain really looks like it's this piece right here. Okay, so as far as individual equations go, we can graph both of these without too much difficulty. This is really just a transformation of our cosine function, a transformation of our sine function, and then I'm explicitly pointing out there we go, the restricted domain. A lot of the fun in these problems comes from now the conversion to a parametric equation, right, or a parametric curve, which means that I'm not interested in each of these individually, but I'm really interested in them as they trace out points in the XY plane, right? So I'm going to transition from these two pictures to this one picture down here that's given in terms of the XY plane. And here the parameter t is sort of hidden in the picture in the sense that it's not explicit, but it's sort of implicitly implied with how our curve is traced out in time, right? So I sort of mask the parameter t in this picture, and I'll have to sort of just see it through the arrows that I draw or the individual points that I plot here. So let's sort of explore this in action. Again, I am most interested in this red region going between t equals pi over 2 to t equals 3 pi over 2. And in each of those cases, I'm interested in the pairing x of t comma y of t. And so that's what we're really trying to plot here. So let's start by plotting 3 points at t equals pi over 2. And that's going to be our first moment in time. Our x-coordinate is up here at a height of 1, 2, 3. X-coordinate is up here at a height of 3. And our y-coordinate is here at a height of 1, 2, 3 as well. Right, so again, our x-coordinate is at a height of 3, our y-coordinate is at a height of 3. So at time t equals pi over 2, the corresponding value that I'm interested in the xy plane is going to be, right, throw some axes on here, it's going to be at that height, or at that point of 3 comma 3. So that is the point we're at time pi over 2. Okay, that's one point that we've plotted. Another point we could plot, just because it's easy on the picture, is the point pi, right? So at time pi, what is our x-coordinate and what is our y-coordinate? Sorry, I don't know why it keeps doing that. What is the x-coordinate and what is the y-coordinate? So the x-coordinate, right, at time pi, that's going to be down here. That's at its lowest point. That's at a height of 1. And the y-coordinate, right, well, that's going to be here at this midpoint, right? And that's going to be also at a height of, it turns out, a height of 1. Right, that's because our x-coordinate has sunk 2 units, and our y-coordinate has also sunk down 2 units. So our height here at time pi, we will be at the point 1 comma 1, and that's where we'll be at time pi. Okay, and so if we just plot 2 points, we get sort of a slightly misleading picture, right? It sort of looks like, or has the potential to look like, this is just a straight line between the two, right? As I go forward in time, my x value is decreasing, my y value is decreasing, and so it seems like both of those should just be decreasing in this kind of straight line direction here. It turns out that will not be the case, as we can see with some close analysis, right? Notice my x-coordinate will start off by sinking, relatively quickly, and then it will sort of sink less quickly. So our x-coordinate, right, I should say here, this graph, we start off relatively steep going down, and then we kind of level off, and we go less steep until we get down to this height of pi. That will correspond with my x value decreasing quickly, and then decreasing less quickly. At the same time, my y value started off by not decreasing that quickly, right? The slope here was not that great, but as I approach towards pi, that rate of decreasing, it started off slow, but it sped up, and got relatively quick by the time we got here. So that means that my x-coordinate decreased quickly and then decreased less quickly, while my y-coordinate decreased less quickly and then decreased more quickly. And so sort of taken together, we have this arc in which at first my x value is the one that's decreasing faster, and then later on my y value is the one that's decreasing faster. And so we'll end up with an arc that kind of looks like this. And I'll just go ahead and sketch that in. Okay, the final point that we want to plot is going to be at the point 3 pi over 2. That's our ending point. And notice at our ending point, 3 pi over 2, our x-coordinate has increased again. It is back up to 3. So our x-coordinate was decreasing, but now it's going to be increasing, and it's increasing to 3. So that's going to be an x value of 3 down here. At the same time, my y value continues to decrease, and it decreases all the way down to a height of -1. And so if I wanted to plot that point, that would end up being what? So an x value of 3, but a y value of -1. That would be somewhere down here. And again, we recognize that this is not just a straight line from one point to the next, but instead we're going to see that our y values start off decreasing sharply, and then they decrease less sharply, they level off, while at the same time, my x values start off increasing relatively slowly, and then they pick up speed and go faster. So what that might look like is we start off with a faster decrease in y, and then a steeper increase in our x value. And when it's all said and done, perhaps not too surprisingly, what we see is that we have a semicircle here, ranging from this point up here all the way down to this point down here. This was the final point at time t equals 3 pi over 2. And so we end up with this, this semicircle. Okay, so maybe first, any questions on graphing this picture, or taking these two pictures and combining them into this third picture down here? Any questions about any of that? Okay, cool. So a couple of things just to point out. One, I said earlier that this, this parameter t kind of gets obscured in the final picture, and that's true, right? Other than explicitly pointing out where we were at different moments of time or at different t values, this picture does not really reference t. There are different ways we can try to reference it. The most common thing that we'll do, and that I would encourage you to do, is to draw a tiny little arrow as we go. At minimum, this indicates the direction of the parameterization. So it tells you that as we increased our parameter, we went in this direction here, right? We started up at the top and we went in the downward direction. If nothing else, that will distinguish this from the curve that is parameterized in the reverse direction, starting at the bottom and then going up. That is worth pointing out because maybe point number 2, our parameterized curve, or any parameterized curve, has the potential to have multiple parameterizations, right? So this was a parameterized curve that traced out a semicircle, but there are different parameterizations that I could have used to trace out this exact same semicircle. And that's kind of cool and kind of a rabbit hole that I love, but we probably shouldn't fall into. I'll point out, for example, that if I had introduced the equation x equals 3 plus 2 cosine of, and now instead of t, it was t over 2, and y equals 1 plus 2 sine of, again, not t, but t over 2, what we would get here is a parameterization that traces out the exact same semicircle, but does so at half the speed, right? In a slightly adjusted window of time. So at this point, this would have been in the purple world, this would have been at time t equals pi. That would have been our starting point. And by the time we got to this ending point, this would have been at time t equals 3 pi. Right? And so under this adjustment, I would have traced through this entire thing, not in 1 pi units of time, but in 2 pi units of time. And so it would have gone at half the speed. It would have gone twice as slow. That's a little advanced. You don't have to immediately make that recognition, but this is just maybe to plant a seed that there are multiple ways we can parameterize the same curve. Oftentimes by making small adjustments like this. This is a topic that I personally love and that will be covered in more detail in Calculus 3. And if I get to teach it anytime in the near future, my sort of advanced geometry class, sort of the geometry of curves and surfaces, right? Or a differential geometry class, similar to the one that I taught this past fall that I know a number of you went to the poster presentation of. So there's a lot that we can talk about in terms of parameterized curves and different ways to express them. And it's tons of fun. Okay, rabbit hole avoided, more or less. Let's jump into another kind of problem. So this is, I think, problem 2 on the activity sheet. This is a super cool parameterized curve, a very famous parameterized curve called a cycloid. A cycloid is a curve that is traced by a point on the circumference of a rolling wheel. So the way that I love to think about this is if you take a bicycle wheel, you put like a little LED light on it so that it glows in the dark, and then you go ride your bike at night, you'd see that LED light sort of like tracing out this cycloid if you were looking at the bike sort of like from the side, right? So the bike's past you, you would see this cycloid being traced out. The cycloid ends up having this really interesting shape. It's not quite a semicircle, though it kind of looks like it, where it traces out this curve, and then it has this sharp point, and then it continues, right? So we could ask the question, how can we parameterize this? We have this clear sense of literally a particle or an LED light or what have you, tracing out this curve in time. So maybe at time equals 0, it's down here. As we trace forward, it's going to be at, at this time. So yeah, at different moments in time, this particle is at a different point on this on this curve. Therefore, this should be ripe for parameterization. And so how can we parameterize this? Great question, tons of fun. Again, this is something that we explore in my differential geometry class early in the semester. Let's explore this here in Calc2 at the end of the semester, and let's figure out how we can parameterize this. And the clever thing that we can do is we can make this observation, which will get fleshed out again in Calculus 3 when we learn more about vectors and how vectors work. But what I will say is that we can actually trace out 2 different parameterizations here. Or we can trace out this parameterization. We can trace out the parameterization of 2 separate elements of this picture. So we can trace out, and maybe we'll do this in red, we can trace out the parameterization that describes the wheel. Whoops, that's a red box. Where's my red pen? That traces out the wheel moving forward. Right, as measured from the center, or from its center. So we can trace out the wheel moving forward as measured from its center. plus, and then we can add on to this a parameterization of the LED light or the particle. Ooh, still red. In blue, we'll do that. We can trace out a parameterization or figure out a parameterization of the LED light or the particle spinning around the wheel. Right? And the idea is going to be that at any given moment in time, I can figure out, yikes, at any given moment in time, I can figure out where the center of the wheel is, right? And I can sort of figure out that position right there, right? Where that center of the wheel is as referenced by the origin. Plus, I can figure out the current location of the particle as referenced by spinning around the wheel, so as referenced from the center of the wheel. And when I add those two positions together, I am going to get the actual center of, or the actual location of the particle itself as measured from the origin, right? So in other words, I can take the wheel's center position plus the particle's position relative to the spinning wheel. And by adding those together, I can get the location of the particle sort of in space, and that will give me the parameterization of the cycloid itself. So kind of cool, kind of advanced sort of idea here. When I talk about adding these things together, it's not entirely clear what I mean by that, but it will ultimately be the adding together of the x of t's and then adding together the y of t's, right? So I'll get in red a position x of t comma y of t, and then in blue, I'll get another position, let's call it x2 of t, y2 of t. And then by adding these together, the position of the cycloid will be the first x plus the second x, and then the first y plus the second y as a function of t. So this idea of sort of deconstructing our picture in this manner, adding things together component-wise, so adding the x's together, adding the y's together, this is an idea that will be explored much, much further and in much more detail in maybe any physics classes that you take, but then also in Calculus 3. When we begin looking at expressions in the xy plane and breaking them down into core components. In short, this will introduce an idea called a vector, and Calculus 3 often involves the calculus of vector-valued expressions. So this is sort of an idea that will become fully formed in Calculus 3. For now, though, let's think about what's happening here. And I want to break this up into two pictures. So first of all, we have the wheel itself in space, right? The wheel is this circle, right? And even though the wheel is spinning and the particle on the outside is moving around the wheel itself, right? If I ignore its spinning nature and I just look at how it's going, the wheel is just going straight in this direction in time, right? And when I measure the center point of the wheel is starting at a given height. And as we go forward in time, its height is not changing. The only thing that's changing is its x position, or the position of its x coordinate. You could say that this conversation is an x position in a certain sense. But anyway, we've got here, so if we call this wheel a wheel of radius a, right, to make this a little more explicit, let's call this radius a. Then the height of the wheel, right, that y coordinate is going to be a, and that's not going to change, right? So it's going to it's going to be at height a. unchanging. The x coordinate is going to change in time. It's going to move forward in time. And now we have to think about the speed at which the wheel is rolling, right? So if we imagine that this wheel is rolling at unit speed, it moves forward 1 foot every second, or 1 unit every second, then by the time it, let me see, is that right? Is that right? Yeah, then by the time we go forward 2 pi units of time, we would have, hang on, let me back that up. Let me think about that. Pausing. Let's do this. I don't want to get, I'm worried I'm going to get bogged down in details here, and I realize I did not completely work this out, so I don't have the notes right in front of me. To avoid making a silly mistake, I'm going to assume that this wheel has a unit radius, right? So the radius is equal to 1. So in that case, the y-coordinate is equal to 1, and our x-coordinate moving forward in time will simply be t. It'll be 1t. Right? So what that means is as I go forward in time, by the time I've gone 2 pi units of time, my wheel will have completed 1 full rotation, and I will have gone forward 2 pi units of distance, right? In other words, over 1 full rotation, my wheel, every single point on the circumference of my wheel would have touched the ground down here. I will have gone forward 1 complete rotation, and that means that I would have gone forward a distance equal to that total circumference of the wheel. So every single point on the wheel touched the ground once. We've rotated around and we're back at this new point 2 pi units in the future. So our y-coordinate in this case would just be 1. Our x-coordinate in this case will just be given by the parameter t. So at time, say, at time t equals 2 pi, I will have gone forward 2 pi units in time. Okay, and so what that means is when it comes time to parameterize this curve, this red curve, right? Again, the red curve is just this one right here, the one that starts here and moves forward. It's measuring the center of the wheel. That would just be given by the equation t, comma, 1 as my parametric equation, or my pair of parametric equations, right? And so that's the center of the wheel. Next, we have to think about the particle spinning around the wheel. And for that, we actually need a slightly different picture, right? The picture that we really want is this picture. It's going to have our wheel, right? The center of our wheel is going to be sort of the center of this picture. And then our blue point is going to start off at the bottom, right? We're going to start off down here. And then as we go forward, it's going to trace a circle around the center of the wheel, right? Because it's going to trace around the wheel going in this direction. So it's going to give us, or it's going to ultimately trace out a circle of radius 1 over the course of 2 pi units of time. So it's starting down here at the origin, right? It's starting at the bottom of the wheel, and over 2 pi units of time, it'll trace itself up in this clockwise direction. It'll hit the top, it'll keep going, and after 2 pi units of time, it will be back at the bottom. That corresponds to starting down here and then tracing up in this direction. Okay, and so the question becomes, how can we express that using these new parametric equations? Well, as we've seen, actually, as we saw in the YouTube video, we can trace out portions of a circle by using sine and cosine as our two equations, right? As our x of t and our y of t. And so now the question just becomes, how can I configure the sine and cosine function to make sure that I start at the bottom and trace up in a clockwise manner? So let's think through this a little bit. I want to start at the point where my x-coordinate is 0 and my y-coordinate is -1. And let's focus on the x-coordinate first. So for my x-coordinate, right, if I want to graph x as a function of t, my x-coordinate starts at 0. Here we go, starts at 0, goes to -1, back to 0, goes to +1, back to 0, right? That's my x-coordinate tracing out that pattern. And I can graph that as x-coordinate starting at 0, going down to -1, 0, +1, 0. This looks like the sine function, but it looks like the sine function that's been flipped along the x-axis, right? Or across the x-axis. So it's our sine function that's flipped. And so we can think about this as x of t equals negative sine of t. So x of t equals negative sine of t. Similarly, if we wanted to graph the y-coordinate, maybe I'll write this up here to just give myself some more space. X of t equals negative sine of t. And then to graph our y-coordinate, right? We've got t, we've got y. Our y-coordinate starts at -1, increases to +1, and then goes back down to -1, all over the course of 2 pi. So starting at -1, by the time we get to pi, we're at +1. By the time we get to negative pi, we're back at -1. So that looks kind of like this. All right, and again, probably didn't frame that beautifully, but again, we can see that this exhibits the behavior of the cosine function, except the cosine function starts at 1 to -1 to 1. This function is -1 to 1 to -1. So this actually looks a lot like the negative cosine function. And so y of t equals negative sine of t. No, what did I just say? Sorry, y of t equals negative, I said it correctly and then I wrote it incorrectly, negative cosine of t. Negative cosine of t. Okay, so coming back to our original picture then, to get this expression of tracing around a circle, we do want to use sines and cosines, but to start here and to go in a clockwise direction, we'll want to have the expression negative sine of t, comma, negative cosine of t. All right, and then to get the cycloid, right? So to go back to our original picture, I now have these two components of the picture. I have the wheel moving forward, and I have the particle tracing around the wheel in this counterclockwise, this clockwise motion. And so the overall cycloid is what we get when we add those two together. And so what we finally get here is our parameterization in which our actual x of t for the cycloid is given by, what do we just say? So it's going to be t minus sine of t. And then our y-coordinate, our y, will be given by y of t equals 1 minus cosine of t. Okay, and taken together, those will actually trace out our cycloid. Any questions about that, right? This was a sort of more advanced question in which we had to explicitly try to break down our parametric equation into individual pieces and then add them together. Ooh, okay, and Alex asks, where does the 1 come from? Great question, thank you for asking. So the 1 came from this picture down here. Specifically, we made the executive decision to make I made the executive decision because I was worried about making a mistake, of making our circle unit radius, right? And to do that, or when we did that, we ended up with this height being 1. So when our circle was unit height, here it's resting on the ground. So this is the x-axis. So the center of our circle here had to have a height of 1. Right, that's just because the radius of that circle was 1. Love it. Thank you, Alex. Did that answer your question? And any other questions? Any questions?
Oh, how did on the second graph that we drew, how did we know that we started at -1?
Oh, that's a great question. Thank you, Chris. How did we know that we started at -1? So that was a choice. I went back to this original picture, and I saw that right here, we were starting at the origin. So our picture here sort of began at the origin. And what I imagined, though it's not explicitly drawn on this example picture, I'll just go ahead and draw it. I imagined the same circle. We see it superimposed several times. I imagine there being a circle, or an awkward egg. I imagine there being a circle here, right? And at time 0, the center would have been here, and the point would have been 1 unit directly below the center. So that was where I decided that at time 0, where we were starting, we would have to have our particle in the down position, right, which is 1 unit below the center of the circle, and that's where that -1 came from. Love it. Any other questions? Okay, I want to try something. I'm calling a small audible, and I haven't prepared this, so it might be a disaster, but I'm confident it's going to be amazing. I'm going to stop sharing my screen for a second. Okay, stop share. And then I'm going to, open up Desmos here. So share my screen. Let's jump over to Desmos. And my hope, so Desmos is my favorite sort of go-to online calculator / grapher. You might have noticed it's what I use for a lot of the pictures in the activity sheets, just because it's really intuitive. And what I hope I can do, fingers crossed, is I hope it's intuitive enough that I can just graph our cycloid and see that it actually traces out what we want it to. So first of all, I hope everybody can see this. Let me know if you can't. I think I shared the screen correctly to Desmos. And what we want here is we want our x-coordinate, which we said was going to be t minus sine of t. We'll add a slider for t here in a second. So t minus sine of t, that was our x-coordinate. And our y-coordinate was 1 minus cosine of t. Okay. Okay, and so let's see. So hopefully you can see this picture right here. And what we'll see, let's make the dot purple to align with our picture from before. Can I make it bigger? Label. Okay. We'll have that label there, and we'll throw on projector mode. That makes it nice and bold for you. So as we go, at the moment, t is 0. As I flow forward in time, let's see what happens. Ooh, so cool. Look at that. So notice it is exactly tracing out the cycloid that we expected it to. I'll zoom out a little bit so we can see the entire window. All right, so as time goes forward and backward, this particle is actually tracing out the individual points that we expected it to in the cycloid. Here, it's going from -10 to 10, but I think we could adjust that to go from 0 to 2 pi. And that's great. That's really cool visual representation that we've actually gotten this correct. If I do this, 0 less than t less than 2 pi, does that do what I want it to? No, unfortunately not. Okay, so I was hoping it would trace out the actual curve and we'd be able to just see it there. But seeing the particle actually move through and trace out the parameterization, if anything, is even cooler. So Yeah, awesome, awesome visualization that says that we got this correct. So cool. Oh, I'm so glad that worked. Any final questions about this example? Okay, well, with the time we have left, I want to focus on these final few problems. And here's where we can bring some of our calculus intuition back to play. Let's say we have a parameterized curve. So that's something of the form x of t comma y of t. And I'm just going to denote that using a single thing, c of t. Usually c stands for curve in this case. So the curve at time t is equal to x of t comma y of t. Let's assume that x and y are differentiable functions and that x prime of t does not equal 0. It turns out that we can calculate the slope of our parametric curve at a given time by computing y prime divided by x prime of t. And the justification for this is as follows, right? The slope of a curve is typically given as dy over dx, right? And notationally, I can think of that as dy over dt, right? So that's the change in my y function with respect to a small change in time, divided by dx dt, the change in our x value over a small change in time. And that will translate down to x prime of t over y prime of t. And so the picture that we can have in our mind is this. Let's draw a quick example curve. So let's say that our c of t, that's my straight line still. Let's say that my c of t kind of looks like this. And let's say that I'm moving in this direction in time. Right? Well, I could choose a given value, a given t value, and its corresponding x coordinate and y coordinate. So let's choose t equals t sub 0. And at time t equals t sub 0, let's pretend I'm right here, which means that this is my x coordinate at time 0. So that's x of t sub 0. And this is my y coordinate. That's y of t sub 0. So we've got our x coordinate, we've got our y coordinate, and then let's imagine what happens as we go forward a tiny bit in time, right? So again, we're expressing this as sort of dy over dx, that's tiny change in y divided by tiny change in x, but what it really is it's dy over dt over dx over dt, so that's expressing how our y value changes with a very tiny increase in time, divided by how our x changes with a very tiny increase in time. So I can imagine now not picking time t naught, but I could imagine picking a very tiny point just a little bit further in time, maybe time equals t naught plus some tiny h, right? So some small little increase in time. If I increase my time just a teeny tiny bit, what I'm going to get is that my x value changes in time. So I'll end up with this new value, right? That's x of t naught plus h. And I'll end up with a slightly changed y value, right? And that's going to be y of t naught plus h. And so if I then calculate the difference, so dx over dt and dy over dt, that will be like this tiny change in y values divided by this tiny change in x values. And that will give us this slope here, right? And as I let my h go to 0, sort of recalling our limit as h goes to 0 definition of the derivative, I get this slope, which could be thought of as simply this y derivative, again, limit as h goes to 0, divided by this x derivative here. Right. So if we wanted to get more formal than that, which, yeah, looking at the time here, to get just a tiny bit more formal than that, again, we're sort of near the end of Calc 2, so it's fun to have some throwbacks to Calc 1. I could express this fraction as, right, this was a y of t naught plus h minus y of t naught divided by an x of t naught plus h minus x of t naught. What I could do if I wanted to is I could not change this fraction at all by throwing on two tiny little h's here. And then I'm taking the limit as h goes to 0 of all of that, right? So this is really our original definition of the derivative, the limit definition of the derivative. And according to our limit laws, if that denominator does not equal 0, so if x prime does not equal 0, I can turn this into the limit as h goes to 0 of the numerator divided by the limit as h goes to 0 of the denominator. And that is truly, in this numerator, that was y prime, and in the denominator, that was x prime. So there is some slightly more formal justification that we can compute the slope of our parametrized curve by using this equation right here. And this is sort of a theoretical, I should say this is a theoretical aside for justification. So don't worry too much about explicitly memorizing that argument, but it's cool how we, maybe that's what I want the takeaway message to be. It's cool how we can justify this equation by jumping back into our limit definition of the derivative from Calc 1. So what does this mean in action though? Let me go ahead and clear that. What does this mean in action? Well, we can talk about parametrized curves, and here's an example of a kind of cool parametrized curve that does this little loop-de-loop. We can try to find an equation for the tangent line at a given moment in time, and we can try to see at what moments in time will our tangent line be flat. And I think we have enough time to explicitly compute both of these. So let's see if we can do this. Let's give it a try. So time one, or problem one, find a time, or find the equation of the tangent line at a given time. So the equation of a tangent line requires two things, right? The equation of a line, of any line, requires a point that the line passes through, and it requires the slope of the line. And then we can use the point slope equation for a line. So we have to figure out at time t equals 2, what point are we at on the curve? And at time t equals 2, what is the slope of the line there? So let's go ahead and figure both of these out. First, I want to point out that this parametrized curve is flowing in this direction. I don't think that's actually vital to the problem, but I think it's just worth pointing out. As time goes forward, notice our x-coordinate goes from a really large number to, at time 0, it's going to be 0 plus 1. So our x-coordinate's going from a large number down to 1, and then back up to another large number. Our y-coordinates, if t is negative, my y-coordinate starts negative and then grows positive. That's that t cubed minus 4t. So it starts off really negative, sort of bumps up, goes down, and then continues on up. And then by the time I'm plugging in really, really big t values, this y-coordinate is really, really big. So that gives us a sense of flow in this picture. And at time t equals 2, our point will be 2 squared plus 1. So I should say c of 2 equals It'll be 2 squared plus 1, so that's 5. And then 2 cubed minus 4 times 2. So that's 8 minus 8. So that's 0. So the point we're at time 2 is actually the point 50. It means we're actually at this point right here. And that's kind of interesting because this is a point of intersection in the picture itself, right? It's not yeah, because there's a point of intersection here, there's a little bit of ambiguity. So are we at this point where we're going in this direction, or have we already circled around and now we're at this point going in this direction, right? In other words, which direction should our tangent line be, right? So this negatively sloped tangent line or this positively sloped tangent line? Let's find out. So to calculate, so I should say that was our point. To calculate our slope, we want to use the work on the previous slide, right? Which means that the slope will be y prime over x prime. And so y prime in this case, right, our y function was t cubed minus 4t. And so y prime is 3t squared minus 4. Our x prime is just going to be 2t. And at time t equals 2, right, this will become 3 times 2 squared, so 3 times 4. So 12 minus 4 is 8, divided by 2 times 2, which is 4. And so we will get that our slope is actually equal to 2. It's equal to positive 2. And so what that means is that here's our point, here is our slope. It means that we're actually going in this direction. So this is our line, right? Let me draw that one more time. Our line, our tangent line is going to be this one. And then the slope of the line or the equation of the line is given by the point slope form of the line, right? So that was y minus y naught equals m times x minus x naught. So what did that become? That became y minus 0, so just y equals 2 times x minus 5, or y equals 2x minus 10, which, if you look at my picture, it was okay, not great. Should have ended up down here. But yeah, that would be our tangent line in this case. Okay, and so that's how we can approach this problem, right? We have a specific t value that we're interested in, and then we just have to evaluate different quantities at that t value using the point and using the slope. The second question is slightly more intriguing, right? Or slightly harder to wrap our head around. We are asking at what points will the tangent line to the curve be flat? And we can actually interpret this. This is a little ambiguous. Do I mean point as in x comma y? Or do I mean point as in point in time? Right, so do I mean a t value? It turns out we will begin by finding the t values. And once we find the t values, we can use that to figure out the point, like the x comma y point. So really, the key to this, at least initially, will be to examine the point in time. And we can then use that to figure out what the x comma y point is. So at what points will the tangent line to the curve be flat? Well, visually, I can see that there are 2 points. There's going to be some point right around here, and then there will be some sort of parallel point or mirrored point down here, right? Those are the 2 points in which the tangent line will be flat. But how do we actually go about finding those points? Well, we have to think through what tools we have. The tangent line will be flat if the slope of the tangent line is equal to 0, and the slope of the tangent line will equal 0 if the corresponding equation dy over dx equals 0. So we know a flat tangent line, I'll just call it a t-line, a flat tangent line, will occur when, and now what we're seeing here is it will occur when dy over dx equals 0. But dy over dx, well, that was just equal to, right? dy over dx, that was equal to y prime over x prime. And we know that only equals 0 when y prime equals 0. Right? So that fraction will only equal 0 when the numerator equals 0. So now we have actually turned this into a tangible problem. Let's look at our y. Let's calculate y prime. And let's see where y prime equals 0. So in this case, our y was t cubed minus 4t. So our y prime was equal to 3t squared minus 4. And so this really becomes, I should have said this earlier, this is really just a critical point problem, right? This is exactly the same as something we would have done in the middle of the semester, Calc 1. We're trying to figure out the critical points of our y function. And so at this point, we have that y prime equals 3t squared minus 4. We have to see where that equals 0. And so it turns out, I'll put a little box here to calculate this in. Boop. This will equal 0, so 3t squared minus 4 minus 4 equals 0. That occurs exactly where 3t squared equals 4. So t squared equals 4/3. And so we actually do get 2 points. T equals plus or minus the square root of 4/3, aka plus or minus 2 divided by the square root of 3. And so those will be our 2 points in time, right? This point occurs first. So interestingly enough, this positive point corresponds to t equals negative 2 over root 3. Right, so as I'm flowing forward in time, I have my negative times. I hit that point. I hit this point, which will turn out to be t equals 0. And then I keep flowing forward into positive times, and then I'll hit this point down here. So that point occurs when t equals positive 2 over root 3. And then we continue. So these are our 2 points at which our tangent lines are flat. And if we wanted to, we could turn around, take those t values, and plug them back into the original equation. And doing so would give us the corresponding x and y coordinates here. Oh, yeah, a couple great questions in the chat here. So let's talk through that. First of all, Jonathan asks, I guess this is actually the second question, but Jonathan asks, can we explain how I know which is positive and which is negative? That's a great question. And I think the original intuition that I had was that my curve flowed in this direction, right? Even direction's kind of a nebulous word there, but my curve flowed sort of forward in my parameter time, sort of starting down here and then going up, and sort of circling around there. My way to sort of intuit that was to look at my y coordinate here and notice that if my t value was really, really negative, this quantity would be negative. So negative, really, really negative t values would correspond to really negative y values. And really positive t values would correspond to really positive y values. And so that suggested that at negative time, I was down here. At positive time, I was up here. And so just by the nature of my flowing curve, I would have had to start down here, float around, go up there. And once I knew that if I have 2 t values, one of them is negative, one of them is positive, so one of them occurs first. Just the nature of the way that this is flowing suggests that this is the one that occurred first. This is the one that occurred second. So that's why this would have to be the negative time, and then I keep flowing forward, and this would be the one that's positive time, the one that occurs second. Gabrielle asked the question about negative time. Like, that seems a little weird, and that is weird. You're absolutely right. So here's where I said way back at the beginning, I've of course erased it, but I said way back at the beginning that I often use t as my parameter, and I think of it as time. And so therefore, as my time flows forward, I'm sort of tracing out this particle. But really, that's more of not a mnemonic device. That's definitely not the right phrase. That's more of a way to think about how this curve is being traced out as I go forward in my parameter. It's easy to think about that as going forward in time. In truth, though, the parameter is really just a parameter. It's just some number. And I can think about plugging in negative values of that parameter as well as positive values of that parameter. Alternatively, we can think about it like this. I could imagine t equals 0 not to be the beginning of time, but rather sort of like a point that is anchored in time, right? So t equals 0 is a specific moment in time. And in that case, negative t, so my negative parameter, could just be thought of as moments in time that occurred before that. In this picture, it's not explicitly said, but maybe it should be. We can imagine our t values as going all the way from negative infinity to infinity, right? So that's sort of the idea that time or our parameter stretch forward and backward infinitely in both directions. And then in that case, the sort of anchor point is just an arbitrary t equals 0, which corresponds to this point right here in the picture. But I could imagine sort of tracing out backwards in time and tracing out forwards in time to trace out this entire curve that's drawn here. So Gabrielle, hopefully that helps answer that question. In short, yeah, the time, like the notion of calling the parameter time is a little bit of a misnomer. It helps intuitively imagine tracing out this picture, but it doesn't mean necessarily that it has to be time as our parameter. It's really just a parameter that can take on any value, positive or negative. And what we sort of want to think about is, as I go forward in that parameter, which direction am I tracing out my curve? Awesome, awesome, awesome. I'm definitely out of time. There's one kind of cool thing that I wanted to at least mention, and maybe this is something I won't go into detail on, but as it is a Friday and you have a nice weekend ahead of you, and I think the weather is supposed to be, well, a little rainy today, but maybe nice later this weekend, maybe you could find some time, drink some coffee, and mull over this. We have this equation, we have this equation on this slide involving the slope of our line. And on the previous slide, we have this cycloid, a really goofy looking, odd looking curve in which we have these sharp points. So actually, these sharp points are really interesting. And so it's worth exploring. Won't do this in class, but worth exploring what t values occur at these points and what is y prime at that point. What is t? What is y prime? What is x prime? And what is dy over dx at those points? Right, so just a sort of interesting thing to mull over. Things can get weird when we look at these parameterized curves and there are these sharp points that can occur. So what is happening at those sharp points? It's a subject for a future math class. You don't have to think too hard about it, but if you're interested, this is something you could explore this weekend over a hot drink while sitting outside. Or Jonathan, if it's cold outside, if it's hot outside, maybe a nice iced coffee or something. Okay, I'm definitely out of time. I definitely want to stop there. Have a wonderful rest of your day, everybody. Have a great weekend. Don't forget to take a quiz that's on Moodle today. So that will be, open for the rest of the day, and begin sort of thinking about the test that is coming up next week. Otherwise, yeah, take care. Have a great weekend. I'll see you all next time.
Thank you, you too.
Yeah, thanks, Jose.